That's right, we're talking about free falling. All right, so what exactly happens when we're talking about free falling? Well, free falling means the only thing that's really acting on something is the weight itself. In other words, force due to gravity is the only thing that's acting on that. For example, Wile E. Coyote right here, what's going to happen? He's going to fall. The only thing that's causing him to fall is his own weight. So the acceleration of gravity is going to act on him, and he's going to fall to the ground. All right, so what happens when an object falls? Okay, so we're talking about free fall. So what exactly happens? Okay, gravity causes the object to accelerate towards the ground. We kind of talked about that before because, remember, objects are going to accelerate due to gravity because gravity is an acceleration, and the unbalanced force is its weight. So does the mass of the object matter? Okay, talk about that in just a second. Acceleration due to gravity is the only acceleration on the object. There is no other acceleration in a free fall. Okay, does the mass of the object matter? Once again, it does not matter. The mass of the object does not matter. All right? So, but why do I see things fall at different rates? Okay, because you've probably seen things falling before and they fall at slightly different rates. Okay, we talked about before when we had a free body diagram, we had something going down and you might have something going up. For example, we would have the force due to gravity down, or the weight, and we could have air resistance working up. Push the object up for this reason, you might have something not accelerate at the full rate of gravity. So for what we're talking about, though, we're going to say there is no air resistance. This is going to be the ideal situation. So the acceleration due to gravity, like we talked about before, have a symbol of g, and right here we have negative 9.8. We might start using this negative 9.8 more, mainly because when we say negative, we're talking about a direction, and that direction is down. Because we already know that the acceleration of gravity is down, but this is just a way we're going to remember that. We're trying to find out velocities and things later. So that's why the negative sign is there. So once again, it's always directed towards the Earth, which in our frame of reference is down. You already talked a little bit about frame of reference with last night's homework. So that's, once again, that's why we give it a negative value. So what's happening in this picture here? So right here we have a picture of an object that's dropped, okay, and then it's taken, the picture's taken every 0.05 seconds, and as you can see, well, I mean, kind of look at it. What's happening between the pictures there? The distance it falls each time period actually increases. So right here you can barely see where the bottles, it just pretty much seems to be in the same spot. And then down here you can actually see there's a little bit of space, a little bit more space, and even more space in between the bottles as you go down. Okay, this is because as the object goes down, it continues to accelerate. Okay, we'll talk more about that with another slide in a second. So this, if it's accelerating, what continues to happen to the speed then? Okay, the speed continues to increase over and over again. So the object is going faster. So let's say if we had 1, 2, 3, 4, okay, different spots here. It's going to go the fastest at 4. It was going a little bit slower at 3, a little bit slower at 2. When we first started it, before we let go right here, it's actually at rest. So the initial velocity would be 0 meters per second. Just want to make sure you know that anytime we drop an object, its initial velocity is going to be 0. So here's a little better example, kind of visually, of seeing what happens as you go along. So once again, in that, we started with 0 because we were at rest. As we're going down, every second, okay, it's going to be getting faster and faster. So in the first second, it's 9.8, all right? The second 19.6, so that makes sense because 9.8 times 2 is 19.6. As you go down, then once again, now the third second, it's much faster. Okay? And also, you see all of these D, sometimes we'll refer to this as delta Y. We'll talk more about that as we get into the equations. But if we're dropping something in free fall, it's moving in the vertical. So therefore, refer to it as delta Y, which just means change in the Y direction or the Y displacement. So that D stands for displacement. All right? So right here we see the equations for free fall. Okay, these should look familiar because they're actually on your formula chart. Okay, but the important part, kind of a difference we're going to see here, is when we're talking about acceleration, the acceleration is due to gravity. Okay, so this A is really a G, right? Okay, so if you want to write that, if that helps you, just realize these A's or acceleration of gravity, so it's g. Now remember, on your formula chart, it's going to be an a, so that's why I've left it an a here. Once again, we're going to refer to that as negative 9.8 meters per second squared, the acceleration of gravity. Okay. So now free fall kind of leads into another topic we're going to get into this unit, and that's called projectile motion. Okay, projectile motion is an object with a horizontal velocity and a vertical velocity. Okay, because earlier we talked about, so once again, free fall, it's moving straight down. So you're probably familiar with something, if you throw a ball or something like that, if I were to shoot something, okay, if I was up here and I threw something, okay, it would go down and land here. Okay, so now we're going to talk more about projectiles. Projectiles is really a thrown object. All right? So what goes up must come down. For example, here's your basketball. Okay, what's really good about this is we're going to talk more and more about what we call V sub x and V sub y. We'll get into that on the next slide. But start realizing, so this is the, so the V sub y would be the velocity in the y direction, see, or the vertical velocity. V sub x would be the velocity in the x direction, or horizontal velocity. And once again, the V sub y, I didn't write the word down, is vertical velocity. All right? So once again, thinking about, talking this stuff through, what acceleration are we seeing there? Gravitational acceleration is occurring there. All right? So what is the speed at the highest point? Okay? So in other words, if we started throwing here, I'm going to draw some vectors here, if you will, because everybody loves vectors, magnitude and direction. Oh yeah. All right. So we have V sub y there and V sub x. Okay, we'll talk more about this in a minute, but the V sub x has nothing really working on it, so it's going to stay the same length. It's supposed to be the same length there. All right. And the V sub y is going to get a little bit smaller because of the acceleration of gravity working down. And in fact, up here, the very top of the path, there is no velocity in the y direction. It's only velocity in the x. Okay, we'll talk more about that as we go. So right here, V sub y at the top of the path is 0 meters per second. Okay, the velocity in the x, if V sub x was, let's say it's 10 meters per second, it's going to stay 10 meters per second the whole time. All right? And then when it comes back down the path, now you'll see this velocity, it'll be the same as it was on the path going up. So these two will be the same right here. And the V sub x is never changing. The whole time we have gravity working down. So kind of looking at these other questions I'm asking here, let's look at them. What is the speed at the highest point of the bounce? We kind of already said that, but reinforce it. The velocity is 0 there. And how about the acceleration at the top? Some people get tripped up by that. This is the acceleration the whole time. It's always accelerating by gravity, always g. All right? Always a g. Anyways. So we kind of already talked a little bit about how there's V sub x and V sub y. So if we had an anti-gravity banana cannon, okay, just work with me here, okay? Be a floating banana cannon. That's pretty cool, right? So the monkey is vicious, so we really want to get him a banana. So the point is, how can we make sure that we make the banana all the way to the monkey? And the monkey's dropping, and we're going to have gravity working down, so how can we make sure that it gets all the way over there? Okay? So would you believe it, if I shot it when he lets go, he could actually meet the banana in the air? All right? So what I've done is I actually took some pictures here of this virtual. Maybe in class I'll slow down for a minute and show you this. It's kind of funny to look at. But the big thing I want you to realize is, once again, the V sub x, which is the red here, is constant. It's a constant velocity, okay? Now the V sub y, which is blue, as you can see here, V sub y there compared to V sub y there and V sub y down there, it is accelerating. Accelerating due to what? Gravity. Okay, it's accelerating because of gravity. So it starts out, once again, initially, right here, V sub y equals 0. As it goes down, it continues to get larger and larger, but V sub x is constant. It's very, very important to remember that. All right, you can pause this if you'd like. I'm going to move on quickly. Projectiles, trajectory, range, and height. You do want to have those definitions down, so make sure you take the time to do that. Pause it and write those down. Remember this equation? We talked about this when we were looking at free fall earlier. It's the same thing, except now we're going to split it apart because we have delta x, which is our range, as you just wrote down a while ago, and delta y, that's our displacement in the y direction. Okay, once again, so we're taking this part of it to solve for delta x, okay, or the displacement in the x direction, taking this part to find delta y. Okay, so we neglect some rules kind of just to make projectiles simpler as we're looking at them. Remember, we're going to say there's no air, we're going to neglect air resistance. We're always working with horizontal projections like the anti-gravity banana can. Remember, we're going to start here and it's going to go down. Okay, there's no acceleration horizontally. Just want to reinforce that. No initial velocity vertically. Height and g are both negative or both positive because why? They're in the same direction. The time it takes to fall is the only common factor. It's the only time we'll see that in both. So the t there and the t there are the same. So if we have a ball thrown at 4 meters per second horizontally from a height, what would it look like? So go ahead and pause it for a second and draw the trajectory of the projectile and also draw vectors for v sub x and v sub y at 4 different points along the trajectory. So pause it, try that. So as we go there, you'd actually see a trajectory, which is the path that it's taking. And then you have v sub x, v sub y. Once again, v sub x is constant. V sub y is accelerating. The main thing I want you to understand is v sub x and v sub y are independent of each other. They are independent of each other. They are independent of each other. How many times should I say it? We'll go with that. That's enough times for today. All right? Tune in next time for some projectile equation practice. Oh, yeah.